Pues buenas noches. Me han traído aquí para que introduzca a nuestra invitada, que para muchos de nosotros no necesita introducción, pero bueno, quizá algunas notas de su biografía. Es una bióloga que hizo su tesis, defendió su tesis en la Universidad Goethe de Frankfurt y durante años ha sido Deputy Director del Instituto de Medicina Espacial en la DLR, en lo que es la Agencia Espacial Alemana. Desde siempre su investigación ha estado dirigida a la radiación. Ha sido una de las pioneras en trabajar en el efecto positivo y negativo de la radiación en la evolución y ha sido también una de las pioneras en diseñar experimentos por los cuales se han expuesto seres vivos a la radiación en el espacio y se ha podido apreciar cuál era el efecto en los mismos. Es una persona muy dedicada a la astrobiología. En realidad yo la conocí cuando la astrobiología empezó a nacer hace ya unos 15 años y desde entonces pues hemos tenido una amistad muy fuerte. Yo respeto mucho a Gerda, en primer lugar por su dedicación. Es una persona que ya en el año 2004 se jubiló, pero continúa en la frontera de la ciencia, trabajando duro, y además es una persona muy generosa con su tiempo y con sus conocimientos. Pero como no me habéis venido a escuchar a mí, sino que hemos venido a escuchar a Gerda, por favor, el suelo es tuyo.
So, thank you very much, Ricardo, for the nice introduction. Thanks to all of you for coming to listen to my talk. And I would like to thank the Foundation BBVA for inviting me to tell you about my favorite field of research. I am very happy to be again in Madrid. And I say again because I have quite a lot of cooperation with scientists from Madrid, with the Centro Astrobiología, where we currently develop an astrobiology roadmap for Europe under the auspices of the European Union. And also we have a joint project with Ricardo Amil and other Europeans studying life in extreme environments in preparation of looking for life on Mars. And there is also a quite long and successful cooperation with Dr. Rosa de la Torre from Inter. And we have studied since many years the adaptation of extreme microorganisms to high altitude mountain areas. And we did that in the Sierra de Gredos. And our test object was a lichen, Rhizocarpon geographicum, and that finally this kind of cooperation culminated in space studies. We have studied this kind of lichen under space conditions, how it was able to cope with this extreme environment. And after such a long day of working in, for us also extreme environment, in the High Sierra it was hot and extreme for us. In the evening, when we sat in front of our cabin and looked at the sky, and then we saw all these stars. And we sometimes asked ourselves, what is going on all these stars? And we know that there are 100 billion of stars in our galaxy, like our sun, or different, more mass or less mass, but 100 billion stars in our galaxy. And we just now, since about 10 years, 15, 20 years, since we know that these stars have many of these stars have also planetary systems. There are planets orbiting around the other stars like in our solar system, the planets orbit around our sun. And that's not enough. There are more than 100 billion galaxies in the universe. And all of these galaxies have also stars, which may be also planets. We do not know. And then is the question, are we alone in the universe? And even if we look from outside to our solar system, as you see here, the Earth would not be visible anymore. First, it would be a pale blue dot, and then it would not be visible. And would this little not visible place in the universe the only place to harbor life? Or is life a cosmic phenomenon, which is not only appearing on our planet, but also appearing somewhere else in the universe? And a certain kind of answer to this question, a very fundamental question, is life a cosmic phenomenon, was given by a Nobel Prize winner, and that is Christian de Duve, who just passed away this year. And he was a biologist and chemist. He got his Nobel Prize for studying the functions in the regulations in biological cells. And he stated that life is a cosmic imperative, and that life would emerge everywhere in a certain stage of either cosmic or planetary evolution if the right environmental conditions, the right physical and chemical environmental conditions would be given and are available. So sometimes the genius, the very intelligent people, they make a statement, but now where to look, how to study this? And this is a mandate which we scientists have got. And so the question is, how can we now find the answers to this statement that life is really a cosmic phenomenon or not? And in order to study this, there are scientists from different fields of research joined together, from astrophysics, from planetology, from geology, even those who look for fossils, paleontology, chemistry, biology. They all joined together in the endeavor to study the origin, evolution, and distribution of life, and not only on Earth, but within the cosmic context, in the context of cosmic evolution. And that might help us to finally come to a more universal definition of life. So if we look at the cosmic evolution, and this is a series of astrophysics and evolution of the universe and the cosmos, so let's make a short quickie about how we think that the cosmic evolution started after the Big Bang. Then very soon already the first protons and neutrons appeared, which then joined together, fused to atoms. We have the first stars quite early in the history of our universe, and finally proto-galaxies which had already stars, and then finally the real galaxies. And we know now, 13.7 billion years after the Big Bang, there is life. We know that this life on Earth lasted already for about 3.8 billion years. So the starting material for life must have been earlier, maybe about 1 billion years after the solar system was formed, when we had the first stars already, the first proto-galaxies. The building blocks for life have already been formed. So the question is, what are the building blocks for life? First, we have to look what is for our life as we have it here on Earth, and what are the most important atoms, elements that form our molecules, our biological molecules, and finally our body. And these are carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus, and we call them all together Schonsp. There are also more heavy elements necessary. You know, for instance, that iron is the central atom in hemoglobin, in our blood protein, and iron and more heavy elements are also necessary. But the main biogenic elements are these which are listed here: carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus. And where are they formed? They are formed in stars. Fusion processes in stars form these kind of elements. At least those biogenic which I have listed here. In order to have the very heavy atoms like iron, the energy in the stars is not sufficient. So you need more energy. And this energy is caused by, provided by supernova. If a very huge mass-rich star collapses and then explodes at the end of its lifetime, then there is enough energy also to produce very heavy elements like iron. And it's that recycling has not invented by mankind. We have already this kind of recycling process in the universe. Stars are born, stars develop further, and stars die and provide their material again to the interstellar medium, and then new stars are formed from it. So what we can say finally, until our solar system was formed, we had already several generations of stars which were formed and evolved and then died again and delivered their material again to the surroundings. So we can say that our life is composed from the ashes of previous stars. But now we have the elements, just carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus. That does not make life. We are not elements. We are built out of molecules. So these elements have to form more complex organic molecules. The word organic comes from history that chemists divided the chemistry in anorganic and organic chemistry. And organic chemistry is the chemistry of the organisms, of the living beings. So let's see what kind of organic molecules could already be formed without life. And this is in the interstellar medium, in the clouds that are between the stars in our galaxy. And there are little grains, and on these little grains there is a very active chemistry. These elements which I showed you before, carbon, hydrogen, oxygen, nitrogen, they condense on these grains, and by the influence of radiation, they polymerize, they form molecules. And you see here kind of molecules, hydrocyanide, formic acid, formaldehyde, and also complex carbon components. How do we know that? That's with telescopes. You can look into the interstellar clouds, and from the spectra that you record, you can determine this kind of molecules. And they look somehow very poisonous. Formic acid you need normally for sterilization, and in former times one used it very much. And hydrogen cyanide is a poison. We cannot breathe it, and we cannot take it up. It would be toxic. Also carbon monoxide would be toxic. So these molecules, which are toxic for life today, were essential precursors for life to start with. And how do now these molecules from the interstellar medium come to a planet where life starts? First, we can say that we have found more than 150 different molecules already in the interstellar medium. So it's really a huge reservoir of this kind of molecules, of which I have given you only a few examples. And now, how do these molecules in the interstellar medium come to the planet? And here you have the picture where you have on the left upper side, an interstellar medium, the interstellar cloud, which somehow starts to collapse. Why does it collapse? There are different reasons. It could be that there is a supernova somewhere not far away, and this gives a big shock pressure so this cloud becomes, collapses. And finally, it starts to rotate and forms a pre-solar nebula. And in the center, it rotates. In the center, you see already, there is a formation of the star. And in the outside, there are all these little grains which stick together and agglomerate. And finally, they make little planetesimals, and finally also planets. So you see here the orbits of the different, of a planetary system that's forming, and in these orbits there's a lot of little grains, but here also then larger planets may appear. So this could be for the Earth, but this could also happen in other solar systems in our galaxy. And the next slide gives you a little bit the whole cycle, and you see again we have a recycling of material. Everything starts in a diffuse interstellar medium dust cloud, where you get these kind of organic molecules. It condenses then, and finally, if there is a supernova or something outside, you get the shock wave and you have the birth of a stellar system. And where the little rocks then become larger and larger through agglomeration processes, and finally you have what we have in our solar system, could be also in other planetary systems. Comets from the outer regions bring the cold stuff, the water, and the organic material to the planets which are closer to the sun and which were too hot during the beginning, so that they could not keep the water and the organic material. And finally, after some period, our sun at least will blow up. It will take another 5 billion years and will blow up and become a red giant phase, and the material will again be then injected into the pool of organics and material in the interstellar medium. Our sun has a lifetime of about 10 billion years. We are nearly at half of it, so our solar system is 4.6 billion years old, so we have another 4.6 billion years until the sun dies, but it will take not so long for the Earth to be habitable, because the sun will expand when it becomes a red giant, and then it will become too hot on the Earth. And so we have to find ways to go to colder places in time. But that will happen in 1 billion years or so, so we do not really need to care about that at the moment. So, discussing this all, we still have to recognize that so far the Earth is the only planet known to harbor life. And that was also expressed by one of the very famous astrophysicist Carl Sagan in his book Pale Blue Dot, where he mentioned that when you go outside and look at the Earth, it's only a very tiny pale blue dot. And the Voyager and Pioneer, I think the Voyager, the Pioneer satellites, which were started a long time ago and went to the Jupiter system, they are now at the rim of our solar system. And when they look back, Earth is really just a very pale blue dot. So let's look at this pale blue dot and what we know about the history of life on Earth. What you see on the left side is the beginning of the Earth. The Earth was first formed close to the sun, like the terrestrial planets, like Venus and Mars. And in that region, it was very hot at the beginning. So all the volatiles, the water, were outgassing, and it took some time until the comets and the meteorites brought the water back to the Earth, because the comets were formed very outside of the solar system, and they brought the water back to the Earth. By the way, did somebody of you see the comet on the evening sky? You can see the comet Ison now, who was just ready for Christmas, but then it went too close to the sun and lost. It was too hot, and everything was outgassing, and the poor comet lost his tail. But when at 6 o'clock in the evening you look at the sky, you see a very bright star, and that is the comet Ison who lost his tail. But it's still very interesting. So, coming back, water and organic materials were brought to the early Earth by comets and meteorites. And then at the same time, you must think the Earth was, then there was a primordial ocean, and there was a lot of volcanic activity, and in all this environment, these organic molecules were processed. It was like a reactor of prebiotic chemistry, and finally there were more complex molecules, and then somewhere, there is the start of the first living cell, still in the ocean, and for a long time life had to continue to develop in the ocean, because the atmosphere and the environment on the surface was not very good for life. Why not? There was no oxygen in the atmosphere. Oxygen was produced by simple algae, we call them cyanobacteria and algae, and by photosynthesis. If you do photosynthesis, you use the carbon dioxide of the atmosphere, and that is converted into biomass. So biomass by the help of the solar light. The energy comes from the solar light, and the hydrogen who reduces the carbon dioxide comes from the water. So the water, H2O, is split into hydrogen that is used for building the biomass, and oxygen is just released, H2O, the oxygen is released into the atmosphere. And that took place right at the beginning already when life started, and then it took some time until there was enough oxygen in the atmosphere, and the oxygen was then photochemically further oxidized by the sunlight and formed the stratospheric ozone layer. The ozone layer, you all have perhaps heard about the ozone hole that is in Antarctica and still coming up in springtime in Antarctica. And this ozone shield protects the Earth and our biosphere against the very harmful ultraviolet radiation of the sun. So this is the history of the Earth. We know the Earth is about 4.6 billion years old. Very soon after our solar system, during the formation of the solar system, the Earth was already built, and the age of life is about 3.5 billion years old. I will tell you why we come to this dating. And so summing up again, we can say that the organic material was brought to the Earth from space by comets and meteorites, and also the water. And there is, we call that prebiotic soup, but this is not like a soup you have in your kitchen where a lot of organics. It's more just a nickname, and there were probably areas on the Earth which were more favorable than for these prebiotic processes. And in addition, there were also a synthesis of organic molecules under the conditions of the Earth, in the atmosphere, in water, on minerals, with the energy available there. Then they formed more complex prebiotic molecules, and somewhere in here, it's still the big question mark, how life started. We still do not know it. We are approaching it now with synthetic biology, but we still do not know. And then there might be even a step in between, an RNA world, and still we come to this protein DNA world of our modern life, and I'll come to that in a minute. So these are the message to give to you. The ingredients for life came from outer space and were also formed in the atmosphere of our early Earth. Why do we know that life started around 3.8 billion years? And there we have to look for the fossils, microscopical fossils. And they are formed if, for instance, in a lake there is mud forming without any oxygen, then in this mud the little organisms die and they will be crystalline with incorporating silicium, and then you have these as little stony memories. You know all fossils probably. You find fossils in many sediments until today. The oldest sediments which we have are 3.5 billion years old, and they are found in South Africa and in Australia. There's another region in Greenland which is even older. It's 3.85 billion years old, but we are not sure whether in this region, where they also have found very interesting indications of former life, whether this has not been changed within the billions of years. It's like criminalistics. You have to look into these areas and to find whether you can see some microorganisms, fossil microorganisms. And this is not easy, but this is one of the scanning electron micrographs that was taken by my colleague Francis Westphal. And what you can see here is 2 micron in the bar, and you can see here these little organisms, and they are in size and shape very similar to microorganisms that still exist today on Earth. And there are a lot of debates whether these are real old microorganisms or whether they had a chance to invade in these sediments by later water coming in. And this is difficult, but Francis Westphal did also an elemental analysis and found that all the essential elements like carbon, oxygen, nitrogen were still located in these tiny little bacteria, fossil bacteria. So far, much for the fossil record. So when we look now for the fossil record, not only for these little microorganisms, but through the whole history of sedimentary rocks we have on Earth, then we can make a kind of biological clock. And you see here the evolution of life in Earth's history, starting with the origin of the Earth about 4.6 billion years ago. Then there is a time where the Earth was still hot and had no real crust, and then the crust came, and then somewhere here, 3.5, 3.8 billion years ago, we date now the start of life. It is worth mentioning that in this period, before the appearance of the first fossils, that we think the beginning of life, there was a heavy bombardment of comets and meteorites on the Earth. And one assumes that these comets and meteorites were very essential in bringing the precursors of life to the Earth. And then these pink here are microorganisms. And you see, during the whole history of life on Earth, the microorganisms persist. Normally one says a species dies out after a certain million of years, but the microorganisms are so resistant, they withstand the ice ages and they withstand changes in the environment. They adapt to very many changes in the environment. We find them very deep below the surface of the Earth in 3 to 5 kilometers depth, we still find microorganisms that are adapted to these special conditions. And then you had the photosynthetic bacteria, here the cyanobacteria, which started to develop photosynthesis, and then after 2 billion years ago, so we are now here, 2 billion, then the oxygen slowly came into the atmosphere, and then you have the algae, the shelly invertebrates, and then vascular plants, and the humans are just a few 3 million years in this whole time scale. So we are a very small part of the whole biological clock. And that may not be the end. It's not that humans are the crown of life. We do not know how that evolves further. The Earth has still some time to develop and let the biosphere evolve. So this is the kind, we should keep that in mind. This is how we think that life evolved on Earth. But let's have a little bit more a look at life on Earth, because we want to go then and see whether we can find life somewhere else in the universe. So we have to find what are the basic principles that are laid down in all life on Earth. So life on Earth is not only us. Life on Earth are the animals, the plants, and the microorganisms. So all this, they differ in size, they differ in mobility, they differ in different kinds of metabolism. Plants can photosynthesize, other animals just eat their food, and so it's very, very varied. But if you take a microscope, or even if you look into the biochemistry, the molecular biology of all these life forms, they are all following the same basic principle. And let's look at these basic principles a little bit, because that might help us to identify then conditions for life somewhere else. So what's common to all life forms? All life forms are built out of cells. They are compartmentalized. Either they are single cells, like the microorganisms, or they are built of many, many cells, like the multicellular organisms, including us. So all life is compartmentalized. It's not a huge mess somehow which is metabolizing. Everything is in little pieces in the machinery that work independently, also together. Then, as I said already, life is all based on carbon as a main element. All the big biomolecules all have carbon as a most important element, whether it's the nucleic acids or the proteins or the membranes, all have carbon as a main element that forms long chains, enables three-dimensional proteins, and so on. Then the genetic code. You all know that the DNA is a very important molecule, because also in criminalistic you can detect with a little DNA sample already a person who has done some harm to somebody, or you can even detect the fathers by DNA analysis if the father is not known. And the genetic code is laid down in all biological systems in the same way, in the DNA. Then we have all in the proteins the same set of amino acids, 20 amino acids, all the same, whether it's a bacterium, whether it's a plant, whether it's an animal, a human, it's always the same set of amino acids. They have also a speciality, they are a special kind of configuration of the amino acids. And the third one is that this information is then transcribed from the parent nucleic acid DNA to the daughter DNA with all the same, the mechanism is the same for all life on Earth, whether it's a bacterium or a human. Also, how you then translate this information of the genetic code to form the proteins, and I show you that then the picture, is all laid down following the same system, whether it's a microorganism or an animal or a plant. And finally, also, we have a food chain interaction, and communication is also very important. So if we look at this transcription and translation process, which I showed you. So we have the DNA, which is a double helix with the genes on it, with a genetic code. And these genes will be replicated into a daughter DNA, and then you have the information, the same information laid down in the daughter DNA. That's a transcription of the information. But there's also a translation of the information from the DNA into the proteins. And for that you need a messenger RNA, so it's a single-stranded nucleic acid. The DNA is a double-stranded nucleic acid. The RNA is a single-stranded nucleic acid, which is also formed according to this genetic code. And then it leaves the DNA and goes to another place. That's a building place for proteins, the ribosomes. Proteins are composed of amino acids, and then they form long chains according to this information from the DNA. They are aligned in a protein, and you see the proteins are three-dimensional, and these are the workers in the cell that do all these enzymatic processes and helps that our whole metabolism goes on. Now it may happen that you have a mutation, a change in the genetic code by some external forces, maybe by radiation or just by accident or whatsoever. And then this change in the genetic information is transferred to the messenger RNA, and it goes further to the building of the proteins, and now it tells the system here to use another amino acid, not that was originally foreseen, but another one. And then you have a mutation, and this mutation might be fatal or a problem for the organism. It might also help them to adapt to changing conditions. So mutations are the motor for evolution. And if there are many mutations, then finally you can come from one species to another species, which is more adapted to the new environmental conditions. And this is really the driver of evolution. And if you look now for all organisms, again we have on the Earth, and compare a certain gene, a certain genetic information, the same genetic information, but which has changed during the evolution more and more, then you come to a kind of phylogenetic tree. A tree which is based on genetic information, and the more two organisms are, the more mutations have been between two organisms, the longer are the branches. And if there are not many mutations necessary from one organism to another, then the branches are very short. And so you can see if we do that for a certain gene, and the same gene which appears in bacteria, in archaea, two kinds of prokaryotes, single-celled organisms, and the eukaryote, that's us. And then you can see that you get a kind of phylogenetic tree. So here are somewhere, I don't know whether you can read it, but of course the animals and are very on the top of this tree. Eukaryotes, that are these multicellular organisms, and what you can see that they all go through, life goes through a bottleneck. And so you can somehow, with this molecular biology genetic tree, you can also come to the conclusion that life started from a very early precursor, our last universal common ancestor, or Luca. And this is very important if we see, when we also want to look for life somewhere else, that life started with microorganisms, bacteria probably, and then it took billions of years, 2 billion of years, until we had the formation of multicellular organisms, and finally the evolution to thinking organisms like us. And I want to quote another Nobel laureate, Manfred Eigen, and he has formulated that self-reproduction, mutation, and metabolism are the necessary prerequisites for natural selection. And that really then leads us to the theory of evolution, which was first laid down by Charles Darwin, when he never knew that there is a DNA and what is a molecular biology. And now, with the modern methods, we can confirm the interesting theory of evolution, which has been laid down already by Charles Darwin 2 centuries ago. So, coming back again to the history of life on Earth, we know now that the microorganisms have existed since the emergence of life, that they are everywhere, and they inhabit extreme niches. So we can use them to look also for life somewhere else, whether we find habitable areas outside of our Earth. And so to answer again, try to answer the question, is life a cosmic phenomenon? And if we look at our solar system, then we see that there is a kind, it's drawn like a green belt, the green one here. It's an area around our sun where for a quite long period of time, that means billions of years, there was liquid water on the surface of the planet. Or it's likely, and especially that's drawn from the distance from the sun, and we call that a habitable zone. Habitable zone is an area where there is a certain chance that there was liquid water for over a long period, because water is one of the essentials for life. We all exist of a lot of water, and water is also not only a solvent, it also participates in the reactions, as I told you, also for the photosynthesis. So in this habitable zone in our solar system, there are Venus, Earth, and Mars. Venus, we know, is too hot. It's 460 degrees centigrade on the surface, so that's not where any kind of organic molecule can persist. The Earth, we know. So what's left? Let's look at Mars. And we have already done a lot of missions to Mars. You see 3 orbiters and 2 Mars exploration rovers, and a lander Phoenix and MSL. They are all still there, so they are not lost. I mean, we had earlier missions, and I will concentrate on Mars, and then Galileo mission went to Jupiter system, and the Cassini-Huygens mission to the Thorn system, and I have also mentioned the Rosetta satellite with a lander that will next year land on a comet which has a very difficult name, Churyumov-Gerasimenko, and because it's so difficult, people say now the comet is a CG comet. So let's look at Mars. If we look at the history of Mars, we have many, many indications that Mars was a wet planet with an ocean probably and a lot of rivers at a very early time, 3.8 billion years ago. And then with time it became more and more dry and cold. There are many reasons Mars why it developed different from the Earth, and nowadays it's quite dry and cold, but we still know there is a lot of water under the surface as permafrost. And especially this region after the Noachian, the early Hesper, in this time here, we know life started on Earth 3.5 billion years ago, maybe earlier. So this is a period where life on Earth started. And that's why the new findings of the Mars Science Laboratory, Curiosity, are so important, because they have found on Mars in this period freshwater lake sediments. So this might be very interesting, that the water persisted on Mars at a period where we know that life started on Earth. So the missions that are interesting, looking for water, because water is one of the prerequisites for life, were the 2 exploration rovers, and they found already very interesting sedimentary rocks and that were formed, minerals that were formed in water, and you see these little spheres, they are produced, hematite spheres, and they call them blueberries, the Americans. They always find nice names for these, but these are not blueberries, these are little minerals formed under water conditions. And the last mission which we have now, and I talked about that already, is the Mars Science Laboratory, and I think Cap and Felipe Gomez is also involved in this mission. And the recent finding that was published in Science is that they found ancient freshwater lake sediments which are from an age which are comparable to the time when life started on Earth. So it's very interesting to go there further and to have to search for life. Europe will have another mission, an rover, which will be launched in 2018, and maybe then I can give you the results of that mission. So, looking back to our solar system, we had now the habitable zone around the Sun, but there are other regions we have found out that there's also liquid water. One is around Jupiter, and have a look at that. That is the moon Europa, which is covered with a thick ice crust. And you see here there are a lot of cracks because there are tidal forces tearing on this ice crust, and we are pretty sure that there is a salty ocean below this ice crust, which is connected to the soil of the inner part of the moon. So this would be a very interesting place to go and study. And nowadays one has also found that from these cracks water vapor is ejected like a cold geyser. A possibility would be that under this ice crust in the ocean there would be places which we have on Earth very deep in the ocean where the inner heat comes out, and where this kind of black smokers are formed with a lot of sulfur and high temperatures, and we know that they are teeming with specially adapted microorganisms. This is another artist view. I think that's a little bit more optimistic, that also some more developed organisms could live in the cracks of the ice crust of Europa. So let's go to another body in our solar system, that's the planet Saturn, and is there also a habitable zone around Saturn? There was a mission, Cassini-Huygens, NASA ESA mission, which went already 10 years ago, about 10 years ago, to this Saturn system, and the European landing sonde was called Huygens, and it landed on Titan, and this is artist view. It did not look like that. Actually, the surface looked like that. And what you can see as rocks are no really mineral rocks. It's frozen ice mixed with methane. So it's a very interesting area. And there are lakes, but the lakes are not water lakes. There are methane and ethane lakes, and we might find the atmosphere is rich in methane. As I told you, the rocks are formed by water ice and methane, and we find a lot of organic molecules also. Might be that finally we find the adenine, not yet found, one of the parts of the nucleic acids. So it seems that Titan, this moon of Saturn is a kind of prebiotic reactor, and if we go there, we can learn more about early life when we had prebiotic processes going on early Earth. But we should not forget, this is a very cold environment, not comparable to early Earth. And there's another moon of Saturn which raised great interest after Cassini saw that there were geysers coming out of cold geysers, out of these rims on the South Pole. And the idea is now these geysers which came out are produced by, this has also an ice shell, produced by subsurface water lenses, might be even oceans of water. And the interesting thing is that Cassini, which passed by this Enceladus, detected not only water and ice particles, they detected also minerals, and they detected organic material. So this is a place where organic material is really produced on another body of our solar system. It's the first body of our solar system where we think that's produced in situ. So it's very interesting moon, and probably there will be missions going to that Enceladus. So what I have talked now was our solar system. So that's here. Our solar system with a green belt, with a habitable zone around the Sun, with Mars, Venus, and Earth in this habitable zone. And that's located in the galaxy. You know, our galaxy is a spiral galaxy, quite as a distal arm of our, a spiral arm of our galaxy, about 27,000 light years away from the galactic center. And one has found out that there's really a habitable zone in our galaxy. If you go further out, then the stars do not produce all the elements that are necessary for life. They have only the very light elements. If you go further in, there's a lot of radiation, and you know the center is a black hole, so this is also not very favorable for life. So there is a kind of green belt also in our galaxy. And this is a place where astronomers are now looking for extrasolar planets. And what are interesting interesting stars where we could find planets which might be habitable, and that depends, and I apologize that I have to show you this diagram, but it's easy to understand. You have first, now it does not work anymore. Yeah, you have first the ordinate gives you the mass of the star, and our Sun is a G star, and the abscissa gives you the distance from the star. And you see here, that's our solar system, with Venus, Earth, and Mars lying more or less in the habitable zone. Nobody knew what happened to Venus that it became so hot. There are, of course, models that explain it. This is Mercury, it's outside, and this is Jupiter, also outside. And if you have stars which have less mass than our Sun, then the habitable zone, because they have not so much energy, the habitable zone comes closer to the star. If you have hotter and more mass-rich stars, then the habitable zone would move for outside. So now you have to look at stars around in our galactic habitable zone, which fall in this range. And as I told you, there have already been thousands of stars identified, thousands of planets identified, and there are several systems which have only one planet. We have found stars which have many planets, and you see here the different stars, and that there are several of these stars which have many planets. And then the orbit per day, again, we have here our solar system with the Earth, with 365 days orbiting. And you see that already a lot of planetary systems have been detected which have shorter periods around the Sun, which go much faster because they are also closer. They are easier to detect. And some of them are close to the area where distance from their star where also our Sun is located. So we are in an interesting time, and we have to wait for more information from the astronomers looking for this kind of stars. And if we then look what are really the requirements, so first you need a host star. You need a star that the planets can go around. You need enough heavy elements, that means up to iron, or at least very heavy elements to form terrestrial planets. You need enough time for biological evolution and environment that is in the whole galaxy. It's free of, they say, life-extinguishing supernovae, because a supernova produces so much energy it would blow away all the planetary atmospheres. And this is another diagram which I would like to explain. So this is now not this is a time before present. So we have now here, and we know that the galaxy formed more than 10 billion years ago. It's billions of years. And this is a distance from the galactic center, which I showed you, the galactic habitable zone. And the idea which comes from the authors from Australia, they say in order to find simple microbial life, then we can have old stellar systems. The Sun lies here. It's about 4.6, is that here? Old, but it can also be in young stellar systems. We can find microbial life, because we know that life on Earth started very shortly after the Earth had formed. But if you want to find some people like us, or let's say intelligent life, if we call it, or people who can communicate, then you require to look at a stellar system which is old, so to allow the time for the biosphere on such a planet to evolve to higher intelligent forms. So it depends on what you are looking for. If you look for microbial life and signatures, you can take any kind of age, but if you want to look for life that has consciousness, like search for extraterrestrial intelligence, the SETI program, then you have to look for quite old stars. And I want to finish with another Nobel laureate, and that's Joshua Lederberg. And he has explained why it's so important for biology to make space research and to look and research other planets. He has said that in physics, we first have established all the rules and laws of physics law on Earth. And we found out then with space research that they are valid throughout the universe. The same is for chemistry. All the chemical rules and concepts have been developed first and understood first on Earth. And then we have found out it's valid throughout the universe. And with life, we do not know it. So we can establish some general rules, what are the general principles of life here on Earth, but we do not know whether that's valid throughout the universe. And so we have to go there and to look in order to come to a universal definition of life. And I want to close with one of the pioneers of space, of astrobiology, and that is Juan John Oro, who laid so many foundations for this kind of research we are doing now. He studied mainly in Houston finally, but he is Spanish, and he got many awards. Among the last one was that he became the Marquess of Oro by royal decree. And without these pioneers like Joshua Lederberg, Christian de Duve, and John Rowe, we would not be here where we are now standing in order to research the context of life, origin, evolution, and distribution of life within the context of cosmic evolution. And so with that, I would like to thank you very much for your attention.